Assalamualaikum warahmatullahi wabarakatuh and hi everyone. My name is Mohamed Azim Ismail and along with my members which are Shireen, Natasha, Binti Mohamed Hakim, Balqis, Binti Abdul Hamid and Lim Yee Theng. We are from Group 9 and we are going to present to you about our integrated project for thermodynamic part. So let's go. So the topic that we will cover today is first schematic diagram for our thermodynamic. Second is the assumption that we made. 3. Type of cycle that we use. And 4. Calculation and recommendation. So the first one is schematic diagram. As you can see here, this is our schematic diagram for steam power plant. So our diagram will start at the furnace and end to the lake. So let me show you how this works. So the water from the furnace will go through the boiler and then the boiler will produce a hot stream and will flow through the 29 steam turbine and 7 generator. And then the hot stream will go inside the cooler and then the waste from it will go to the lake. Meanwhile, the cool stream from the cooler will pump into 18 pump and then will go through back to the boiler. And this process will cycle and cycle. So that's how steam power plant works. Now let's move on to the second part, which is the assumption. In order for us to solve the calculation, we have made several assumptions. So the first assumption is the change in kinetic energy and gravitational potential energy is negligible. Second is the process is in steady flow. Third, the mass flow rate of the stream entering the turbine is 150,100 kg per hour. Fourth, the turbine is well insulated. Fifth, efficiency of pump is 85%. And lastly, the pipe is frictionless. Moving on to the next part, which is the type of cycle. So for the type of cycle, we use Rankine cycle. So water is being pumped from low pressure to high pressure at constant temperature. The high pressure liquid enters the boiler where it is heated at constant pressure by an external heat source from the anthracite coal to become saturated vapor. The saturated vapor expands through the turbine to generate power. This will reduce the temperature and the pressure of the vapor. The vapor enters the cooler where it is cooled at constant pressure to become saturated liquid.
Next, I'll be showing our calculations and also recommendations. First off, we need to calculate the amount of coal required. In order for us to do so, we will be needing the amount of Q in and also the coal heating value. From our icon simulation, we can get the amount of our Q in as stated in the presentation, while the coal heating value, where we get from a reference, is equals to 30,080 kJ per kilogram. After calculating, we can get that the amount of coal required is 4.62 kg per seconds. We are also assuming that this power plant operates 24 hours per day. Therefore, after times with 24 hours per day, the amount of coal required every day is equals to 399,168 kg. From our icon simulation, we managed to get the amount of steam generated, which is 1,870.216 meter cube per hour. Next, we calculated the power produced by this power plant. In order to calculate the power produced, we use the values that we obtained from our icon, which is the power entering the pump and also exiting the turbine. By subtracting both of the values, we managed to get that the power produced by this power plant is equals to 47.3 megawatt. With the values of 47.3 megawatt, we can calculate our thermal efficiency, which is 34.06%. However, the value of 47.3 megawatt are produced is when we are using one turbine. For our project, we are aiming to produce 1,380 megawatt of power. Therefore, we will be needing more turbines and pumps in order for us to achieve the aim value. In order for us to know the number of turbines that we need, we divide the amount of power that we aim by the actual power that we produce. And by doing so, we found out that we need 29 turbines in order to achieve 1380 megawatt. With that information, considering the amount of turbines and also pumps, we can get that the actual power produced by this power plant is equals to 1389 megawatt. From a reference, we are assuming that the maximum amount of work for generator to receive from turbine is equals to 200 megawatt. Based on that information, we found out that 4 turbines are needed for each generator. And since we have 29 turbines, the total number of generators that we need will be 8 generators. This is the energy balance calculation for the turbine. The pressure at this state is 30 megapascal, while the temperature at the turbine is equals to 600 degrees Celsius. By doing the calculations, we can get that work out by the turbine is equals to 60 megawatt. And since we have 29 turbines, so we need to times 60 with 29, and we can get that the total work by turbine is equals to 1740 megawatt. This is the energy balance calculation for our pump. The temperature at this state is equals to 71.33 degrees Celsius. By doing the energy balance calculation, we can get that the work entering the pump is equals to 1854 megawatt. Considering the number of pumps, which is 18, and also the efficiency of the pump, which is 85%, we can calculate that the actual work is equals to 3926 megawatt. Lastly is the energy balance calculation for boiler. By doing the energy balance calculation, we can get that the Q in of the boiler is equals to 1373 megawatt. These are the recommendations that we recommended in order for us to improve this project. One of it is by using a larger turbine and also increasing the steam to a higher temperature. That is all from us, Group 9A. Thank you.